Saving a lost bat, biologists attempt to save orphaned baby bat. Like, share and subscribe and ring the bell for more videos. The effort spotlights how vulnerable and fragile this species is in its early days. At a glance, it looks like a mix between a chihuahua and a dragon. A baby fruit bat, not often seen up close, was recently taken in by two biologists who attempted to save its life in Borneo. A storm had hit the region only the night before, and they reasoned that the bat was knocked from the tree. No trace of its mother could be found. The bat's care was captured on camera by biologist Fredrik Jutfeldt from the Norwegian University of Science and Technology. Jutfeldt, whose expertise is more with aquatic animals, was leading a group of students on an expedition in Borneo when local biologist Giovanni D'Erasmo found the young creature. It's a side of the species not often seen, cute, cuddly, and helpless, and it highlights just how vulnerable the bats are at a young age. Bat pups and their moms have a special bond. Females typically have only 1 to 2 babies at a time, and fly with their pup under their wings for the first month of its life. It was quite tiny when it was found, maybe a month old, he says. It woke up several times throughout the night, and it needed a lot of contact. Unfortunately for the young bat and its adoptive parents, it died shortly after being filmed. D'Erasmo suspects it was too young to be weaned from its mother. It was fed a diet of banana and soy milk, but at such an early age, it may have been too much for the pup's digestive system. A cuter side to bats, despite not making it. Both biologists feel the rescue attempt showed a cuter side to bats that people don't often see. In Jutfeldt's footage, the pup can be seen using its wings to crawl over human hands more than twice its size. Extended, they look like 2 hands with long, delicate skin membranes spread between each appendage. While bats may not be the first animal that comes to mind when thinking of cute animals, the young pup has all the universal characteristics that make animals adorable, according to research. Scientists have found that big eyes, soft bodies, and large heads make animals and babies endearing. Borneo fruit bats are a common species in the region, but, like the island's other animals, they face threats from deforestation. It's an environmental change Jutfeldt witnessed on his recent trip. There's massive deforestation in large areas and large palm plantations that just kill off everything, says Jutfeldt. You go from some of the most diverse habitats in the world to monoculture with just 1 tree. It's devastating to see this. The biologist hopes the baby bat will be like an ambassador for its species, showing people that bats aren't quite as scary as their reputation suggests. Bats are mammals of the order Chiroptera, with their forelimbs adapted as wings. They are the only mammals capable of true and sustained flight. Bats are more maneuverable than birds, flying with their very long spread-out digits covered with a thin membrane or patagium. The second largest order of mammals after rodents, bats comprise about 20% of all classified mammal species worldwide, with over 1,200 species. These were traditionally divided into 2 suborders, the largely fruit-eating megabats, and the echolocating microbats. But more recent evidence has supported dividing the order into Enterochiroptera and Yangachiroptera, with megabats as members of the former along with several species of microbats. Many bats are insectivores, and most of the rest are frugivores, fruit eaters. A few species feed on animals other than insects, for example, the vampire bats feed on blood. Most bats are nocturnal, and many roost in caves or other refuges. It is uncertain whether bats have these behaviors to escape predators. Bats are present throughout the world, with the exception of extremely cold regions. They are important in their ecosystems for pollinating flowers and dispersing seeds. Many tropical plants depend entirely on bats for these services. Bats provide humans with some benefits, at the cost of some threats. Bat dung has been mined as guano from caves and used as fertilizer. Bats consume insect pests, reducing the need for pesticides. They are sometimes numerous enough to serve as tourist attractions, and are used as food across Asia and the Pacific Rim. They are natural reservoirs of many pathogens, such as rabies, and since they are highly mobile, social, and long-lived, they can readily spread disease. In many cultures, bats are popularly associated with darkness, malevolence, witchcraft, vampires, and death. Etymology: an older English name for bats is Flittermaus, which matches their name in other Germanic languages, for example German Fledermaus and Swedish Fladdermus, related to the fluttering of wings. Middle English hadbak, most likely cognate with Old Swedish nattbacka, night bat, which may have undergone a shift from K to T, to modern English bat, influenced by Latin blatta, moth, nocturnal insect. The word bat was probably first used in the early 1570s. 2-3. The name Chiroptera derives from ancient Greek, chair, hand, and kometeron, wing. Phylogeny and taxonomy: the delicate skeletons of bats do not fossilize well, and it is estimated that only 12% of bat genera that lived have been found in the fossil record. Most of the oldest known bat fossils were already very similar to modern microbats, such as Archaeopteropus, 32 million years ago. The extinct bats Paleochiroptera extupiodon, 48 million years ago, and Hasonycterus kumari, 55 million years ago, are the first fossil mammals whose coloration has been discovered. Both were reddish-brown. Bats were formerly grouped in the Superordo, along with the tree shrews, Scandentia, Colugos, Dermoptera, and primates. Modern genetic evidence now places bats in the Superordo Lorasiatheria, with its sister taxon Asphera ungulata, which includes carnivorans, pangolins, odd-toed ungulates, even-toed ungulates, and cetaceans. V1 study places Chiroptera as a sister taxon to odd-toed ungulates, Perissodactyla. The phylogenetic relationships of the different groups of bats have been the subject of much debate. The traditional subdivision into Megachiroptera and Microchiroptera reflected the view that these groups of bats had evolved independently of each other for a long time, from a common ancestor already capable of flight. This hypothesis recognized differences between microbats and megabats and acknowledged that flight has evolved only once in mammals. Most molecular biological evidence supports the view that bats form a natural or monophyletic group. In the 1980s, a hypothesis based on morphological evidence stated the Megachiroptera evolved flight separately from the Microchiroptera. The flying primate hypothesis proposed that, when adaptations to flight are removed, the Megachiroptera are allied to primates by anatomical features not shared with Microchiroptera. For example, the brains of megabats have advanced characteristics. Although recent genetic studies strongly support the monophyly of bats, debate continues about the meaning of the genetic and morphological evidence. The 2003 discovery of an early fossil bat from the 52-million-year-old Green River Formation, Onychonycterus finnei, indicates that flight evolved before echolocative abilities. Onychonycterus had claws on all 5 of its fingers, whereas modern bats have at most 2 claws on 2 digits of each hand. It also had longer hind legs and shorter forearms, similar to climbing mammals that hang under branches, such as sloths and gibbons. This palm-sized bat had short, broad wings, suggesting that it could not fly as fast or as far as later bat species. Instead of flapping its wings continuously while flying, Onychonycterus probably alternated between flaps and glides in the air. This suggests that this bat did not fly as much as modern bats, but flew from tree to tree and spent most of its time climbing or hanging on branches. The distinctive features of the Onychonycterus fossil also support the hypothesis that mammalian flight most likely evolved in arboreal locomotors, rather than terrestrial runners. This model of flight development, commonly known as the trees down theory, hold that bats first flew by taking advantage of height and gravity to drop down onto prey, rather than running fast enough for a ground-level takeoff. The molecular phylogeny was controversial, as it pointed to microbats not having a unique common ancestry, which implied that some seemingly unlikely transformations occurred. The first is that laryngeal echolocation evolved twice in bats, once in the Anguichiroptera and once in the Rhinolophoids. The second is that laryngeal echolocation had a single origin in Chiroptera, was subsequently lost in the family Pteropodidae, all megabats, and later evolved as a system of tongue clicking in the genus Rauzetis. Analyses of the sequence of the vocalization gene FOX2 were inconclusive on whether laryngeal echolocation was lost in the pteropodids or gained in the echolocating lineages. Echolocation probably first derived in bats from communicative calls. The Eocene bat Sicaronicterus, 52 million years ago, and Paleochiropteryx have cranial adaptations suggesting an ability to detect ultrasound. This may have been used at first mainly to forage on the ground for insects and map out their surroundings in their gliding phase, or for communicative purposes. After the adaptation of flight was established, it may have been refined to target flying prey by echolocation. Bats may have evolved echolocation through a shared common ancestor, in which case it was then lost in the Old World megabats, only to be regained in the horseshoe bats, or echolocation evolved independently in both the Enterochiroptera and Yangochiroptera lineages. Analyses of the hearing gene pristine seem to favor the idea that echolocation developed independently at least twice, rather than being lost secondarily in the pteropodids. But ontogenic analysis of the cochlea supports that laryngeal echolocation evolved only once. Bats are placental mammals. After rodents, they are the largest order, making up about 20% of mammal species. In 1758, Carl Linnaeus classified the 7 bat species he knew of in the genus Vespertilio in the order Primates. Around 20 years later, the German naturalist Johann Friedrich Blumenbach gave them their own order, Chiroptera. Since then, the number of described species has risen to over 1,200, traditionally classified as 2 suborders, Megachiroptera, megabats, and Microchiroptera, microbats/echolocating bats. Not all megabats are larger than microbats. Several characteristics distinguish the two groups. Microbats use echolocation for navigation and finding prey, but megabats apart from those in the genus Rauzetis do not, relying instead on their eyesight. Accordingly, megabats have a well-developed visual cortex and good visual acuity. Megabats have a claw on the second finger of the forelimb. The external ears of microbats do not close to form a ring, the edges are separated from each other at the base of the ear. Megabats eat fruit, nectar, or pollen, while most microbats eat insects. Others feed on fruit, nectar, pollen, fish, frogs, small mammals, or blood. Anatomy and physiology, skull and dentition. The head and teeth shape of bats can vary by species. In general, megabats have longer snouts, larger eye sockets and smaller ears, giving them a more dog-like appearance, which is the source of their nickname of flying foxes. Among microbats, longer snouts are associated with nectar feeding, while vampire bats have reduced snouts to accommodate large incisors and canines. Small insect-eating bats can have as many as 38 teeth, while vampire bats have only 20. Bats that feed on hard-shelled insects have fewer but larger teeth with longer canines and more robust lower jaws than species that prey on softer-bodied insects. In nectar-feeding bats, the canines are long while the cheek teeth are reduced. In fruit-eating bats, the cusps of the cheek teeth are adapted for crushing. These feeding behaviors are true for both megabats and the microbats. The upper incisors of vampire bats lack enamel, which keeps them razor sharp. The bite force of small bats is generated through mechanical advantage, allowing them to bite through the hardened armor of insects or the skin of fruit. Vision. The eyes of most microbat species are small and poorly developed, leading to poor visual acuity. But no species is blind. Most microbats have mesopic vision, meaning that they can only detect light in low levels, whereas other mammals have photopic vision, which allows color vision. Microbats may use their vision for orientation and while traveling between their roosting grounds and feeding grounds, as echolocation is only effective over short distances. Some species can detect ultraviolet, UV. As the bodies of some microbats have distinct coloration, They may be able to discriminate colors. Megabat species often have eyesight as good as, if not better than, human vision. Their eyesight is adapted to both night and daylight vision, including some color vision.
With